Hello everyone, welcome to MindSpan Education. So this is another topic in the series of calculation optimization for GATE DA. Today's topic is, this is a relatively easier topic and easy to grasp, and of course questions comes from this topic in examination. Today's topic is maxima and minima. Topic name I am writing from the syllabus, whatever the exact name given in the syllabus for GATE DA, I am writing those names. But we will discuss in detail all the connecting topics and derivatives and use of derivative, everything in this topic. So let's start. First, let me draw a graph, then we will understand what I am trying to explain here. Let's draw a graph. This is a function. Let's say this is a function. This is a function fx. At points, let's say this is A, this is B, this is C, and there is no turn here, it simply just went down, and this is, let's say, D. So by looking at this graph, what you can say about its nature, whether it is increasing or decreasing, in which portion it is increasing, in which portion it is decreasing. By looking at graph, intuitively we can easily figure out that from A to B, graph is decreasing, the value of the function is decreasing. When we say a function is decreasing, let's say fx is a function, okay. When we say it is decreasing, mathematically we can write it like this: for fx1 greater than fx2 implies x1 greater than x2. If this condition satisfy, then we say that function is increasing. This is increasing, case of increasing. What this means, let's say, when put a higher point in the graph, then we should get a higher value. If it is increasing function, if we put a higher point, means higher value of x, then we should get a higher value of corresponding f, right? Then we say that function is increasing in that particular interval. So whenever this condition satisfies, we say function is increasing. When you can write opposite of this, if fx1 is greater than fx2, when x1 is less than x2, then we say it is decreasing, right? Mathematically we can describe it like this. By seeing at the graph, we can say if the values are coming lesser and lesser, when we increase the value of x, then we say the function is decreasing. When value is increasing, when we increase the value of x, when the function value is increasing, then we say that function is increasing in that interval of domain of the function. So how do we define this? Just now which part of the topic I explained, it is called increasing and decreasing function. Increasing and decreasing function. This is exact topic, this is what we are talking about currently, increasing and decreasing. When we say a function is increasing, when we say a function is decreasing, based on intuition and based on values that function is producing by putting different values of x. If it is giving us larger value with increasing x, then we say the function is increasing. If it gives lesser value with increasing x input, with increasing input, if it gives lesser value, then we say that function is decreasing. There isn't much in this to understand, right? It's fairly easy. Now let me take an example, then we will understand this in better ways. Let's take a simple example. Let's take y equal to, we can write fx or y, whatever suits, okay. 2 minus x square. Let's take this function 2 minus x square. Then what we can say, let's plot this first. This is x and this is y, and this is inverted parabola since negative x square, and it will start when x is 0, y equal to 2. So it will start from here. Let's say this is 1 and this is 2. It will start from here and the parabola will be inverted like this. It should be exactly symmetric like this, right? Now notice this, at x equal to 0, everything below x equal to 0, this function is increasing. By looking at the graph, you can see the graph is increasing at all the values which are lesser than x equal to 0. And at x equal to 0, something happened. We will talk about it later, just later in this video. After x equal to 0, this function is decreasing. We are getting decreasing function by just looking at the graph. Now, how we can this, by plotting graph, we can see and we can figure out, but this is not the correct way to figure out. If we get the complicated functions, then it will be very difficult to plot it. So how we mathematically define that? Let's see. Let's calculate derivative of this function y dash. We can say y dash equal to derivative of 2 is 0 and x square is 2x minus 2x. So we can write it as minus 2x, y dash equal to minus 2x. This is derivative of this function, okay. Now let's plot a number line. This is number line, this is negative infinity, this is infinity, and this is x equal to 0. So everything, if we put this value here and test whether y dash is positive or negative, for all the value anything less than x equal to 0, if we put here, one negative is already there. So if we put anything at the place of x which is less than 0, then it will become positive. So everything in this region which is lesser than x equal to 0 is positive, will produce a positive y dash, and everything which is greater than x equal to 0 in this region, everything will be negative, will produce negative y dash. So by looking at the graph, we had concluded that function was increasing in region x is less than 0, and here in this, on this number line, we saw that it, for values x is less than 0, it produces positive y dash, and for all values x is greater than 0, it produces negative y dash. Y dash is nothing but first derivative, first derivative, okay. So first derivative of the function is positive in the region x is less than 0. So by combining both of these things, we can say that, what we can say is, for function to be increasing, we can say f is increasing increasing if f dash x, that is first derivative, is greater than 0. We can say this by, I just shown it to you by taking this example using this graph and this number line. So, we can say if first derivative is greater than 0, then function f(x) is increasing in whatever interval we are talking, like it won't be always complete domain, there will be some interval associated that will come based on the nature of the question or nature of the function more accurately, and f is decreasing if f dash x is less than 0, right? If it is less than 0, if first derivative of the function is lesser than 0, at some point, let us say at x equal to c, then we say that at x equal to c, function f is decreasing. If first derivative is greater than 0 at x equal to c, let us say x equal to c, then we say that at x equal to c, function is increasing. But how this happens? Let us see. Let us delve in more detail about this first derivative test. Why it works? Let us see why this works. Why it is always okay to assume function is increasing when f dash x is greater than 0. Let us see. Let us take a graph which is increasing. This is increasing function, right? It is increasing with x and y values. This is fx, and we already know it is increasing function. Now, if you plot a first derivative at point, let us say a1, and this point is, let us say a2, like this, a3, right? Now, excuse me, when you plot this, now first derivative of function f dash x means tangent of at that point. If we calculate f dash a1 means this is slope of the tangent at x equal to a1. So, if we plot the tangents, sorry, this is not exactly the tangent, but it should be tangent, okay. You can notice this, this at every point, this tangents produces positive slope. Positive means if I take tan theta here, it will give me a positive value. M1 will be greater than 0. Similarly, M2 will be greater than 0, like this. So, for an increasing function, whenever we draw a tangent, it produces positive slope. When we draw a tangent, its slope becomes positive with x-axis. So, slope means first derivative. This is exactly what is written right here. When function is increasing, then its slope of tangent at that point will be greater than 0. Similarly, if you take the decreasing function, you will be able to analyze this just like I shown here, okay. So, two things you have to remember: when function is increasing, f dash x will be greater than 0, and when function f is decreasing, f dash x will be less than 0. Now, let us take another example to see it more clearly. Let us take one more example. Let us take y equal to 2x square minus 8x plus 6. Let us take this example, okay. Now, if we calculate y dash, that is first derivative of this function, we will get 4x. You might get confused between fx and y, right? So, let me write this in the form of f only. So let's write this fx equal to 2x square minus 8x plus 6. So this is our function. We calculate first derivative of this function. First derivative 2x square will become 4x minus 8x will become 8 and 6 will become 0. So this will become, if we take 4 common, x minus 2, right? So if we plot this in on number line, x equal to 2 is the critical point. This point is called critical point. I will tell you in detail later in this video. Critical point. We don't know exactly how function will behave at x equal to 2, but before x equal to 2 and after x equal to 2, we know whether it will be increasing or decreasing. So let's put some value lesser than x equal to 2 in the function, in this f dash x. So let's put x equal to 0 here. So it will become negative. So we write here negative, everything here negative. This is number line. And this is positive. If you put, you will get positive. So in this region, you can see in this region f dash x is negative. So we can say that function is decreasing, right? I just correlated in this example right here. Okay. Now in this region f dash x is positive. So we can say function is increasing. Now if we think more about this graph, what we will know about x equal to 2. Function was decreasing just before x equal to 2, means it was going down just before 2, and now it's coming up after x equal to 2. So what kind of graph we are about to get? It will be something like this, going down, and then after x equal to 2 it has started rising, right? So this x equal to 2 will become minimum point at that in this locality. This will become minimum point, minimum, right? So by looking at decreasing and increasing nature of the function, we can also predict what will be the nature of that graph, value of that graph, that function at critical points. So at this particular x equal to 2, in this particular function, it was decreasing before x equal to 2 and it was increasing after x equal to 2. So x equal to 2, so it was going down and then it has started rising. So at x equal to 2 we got minimum point. It's a trough, right? It's not a peak point. It's like a dipping point in the graph. So x equal to 2 will probably give you minimum value of function f. Okay. Similarly, let's take another example where we have more critical points. Then we will get more clear pictures. Let's take another example. This is a concept which is very easy if you understood this properly. Okay. Let's take another example. Let's take fx equal to 2x cube plus 3x square. Let's take some example, minus 12x plus 8. Let's take this. Now what we are going to do, we are going to calculate, first we are going to calculate first derivative. First derivative f prime x will be 6x square plus 3 to 6x minus 12 plus 0. This will give you, if you take 6 out, we will get x square plus x minus 2, right? We will get this. if we further factorize this, we will get x minus x plus 2 and x minus 1, we will get this. Now in this particular case, how many value, if we equate this to 0, what we are going to get? Once, let's see, let me tell you another fact here, is another small concept. When we equate this f dash x equal to 0, then the value of x, that is roots of this equation x1, x2, x3, all these things are called critical points. This is how we find out critical point. Okay, critical points. When we equate this to 0, we will get x equal to minus 2 and 1, right? So we got two critical points in this particular function. So plot this on number line. This is number line. This is minus infinity. This is infinity, and minus 2 will come first, and then 1. Now put some value here. Let's explain, test in this region whether f dash x is positive or negative. Put some value here greater than 1. Let's put 5. So this will become positive and this will become positive. So positive, positive, positive. So f dash x is positive, means increasing. This is an increasing region. For the graph function, this is increasing. In minus 2 to 1, let's put 0. So we get this is 0, and this is 2, and this is minus 1. So negative. So this is decreasing region. And if you put anything lesser than minus 2, we will get this is negative and this is negative. So 2 negative means positive. So this is also increasing. Now just analyze this. What is happening here? First, the function was increasing. First, let me write the intervals where things are happening. Increasing in interval minus infinity to minus 2, and then union means some more intervals included, union 1 to infinity. In this region, function is increasing and decreasing in region minus 2 to 1. Now this is intervals that we figured out by plotting this number line, and now let's see the nature at critical points. At minus 2, what is happening? Function was increasing first, and then it has started dropping after 2. So at 2 we got a peak, right? So at minus 2, sorry, x equal to minus 2, so we can say that at x equal to minus 2, function is likely to produce a maximum value. It may be local maximum or maybe absolute maximum, which we will talk later in this video, but this is a maximum value of the function in the neighborhood. Now at 1, what happened? It was decreasing first, dropping down, and then it started rising. After 1, it has started rising, x equal to 1. So we can say that at x equal to 1, we are about to get a minimum value of the function, right? So relatively this is a minimum point for the function, and this is relatively a maximum point of the function. So by looking at, when you understood the nature of function, whether it is increasing or decreasing, by just seeing the first derivative of the function, we can say that we can figure out whether the any critical point is likely to be maxima or a minima in for that particular function, right? There are other ways also to exactly find, mathematical ways are there to find whether a critical point is maxima or minima. We will talk about that double derivative test in just a moment. Now first you understand this. I am taking more examples and explaining this in detail so that you understand, you get a feel that what derivative is doing with a function, why we are calculating tangents, why we are seeing the curves in the function, right? So this is another example. Now you might have noticed that by putting some value here in this region, we calculated whether the function first derivative was positive or negative. But when there are a lot of critical points, we don't have to put values in all the region. All we need to do is to calculate one region, and then we can interpolate, we can figure out other regions whether it will be positive or negative. So how we can do that? Let's see. This is another concept, and please note this. This is very important. This is called wavy curve method. Wavy curve method. By this technique, this is just a technique, we can figure out on the number line whether a function is going from positive to negative or negative to positive. Let's take one example to show you. Just let me take an example to show you how it works. Let's see. Let's take example f dash x equal to x plus 2 x minus 1 square. All these are in factorization form. X minus 2 cube into x minus 4 to the power 4. Now, if we draw the wavy curve method, what this wavy curve method does is, first we draw a number line. Okay, on this number line, we first write the points. All these critical points, which by equating to 0, we will give roots of this equation. So first we will get minus 2, right? X equal to minus 2, then we will get 1, then we will get 2, then we will get 4, right? 4. So we will take only one point, which is easier for us. Let's take 0. Let's take, for this, by looking at this equation, we can take anything like 5. 5 is easy, right? Or everything will become positive, so it will give you positive. In this all region, we will get positive value of f dash x. Now we do not have to check in all these region, we do not have to put values and calculate. But for saving time, what we can do is, if it is positive and this is the point when we reach, let's draw the, let's say this is positive side and this is negative side. Okay, now this this in this region f dash x was positive. Now we reached at 4. At 4 we see the power was even. So if it is even, then it won't change the direction of the graph, it will still remain in the positive side, so still positive. Now see the power of 2, this is odd, power is 3, which is odd, so it will change. If it is positive, it will become negative. If it is negative, it will become positive. So now it's negative. Now at x equal to 1, even power, so it won't change, it will still remain in the same region. It won't become positive, it will remain in the same region. If it was in negative side, it will remain in the negative side, it won't change. At x equal to minus 2, x plus 2, power is 1, so it is odd, so nature will change, it will become positive. Now you can see, from minus infinity to minus 2, it is positive. Now it's negative, and then negative again, then positive, and then positive. This is how we can figure out the nature of the function in these intervals without putting any, without doing manual calculation by putting these values on the number lines. Okay, this is easier and this is time saving. In exam, you can use this wavy curve method to find out whether in which region the f prime x will be positive or negative. Now if we discuss about the critical points, so it is positive to negative, means it was increasing then decreasing, so this is local, we can say local maxima, positive to negative. This is negative to negative, we don't know what it will become. So negative to negative, we don't know, right? From negative to positive, it was dropping, then increasing. So it's likely to be a minima, local minima. And positive to positive, we don't know what will be, how it will behave. Okay. So this was wavy curve method. Using this, you can know the nature of the function in particular region, whether it will be positive or negative, right? You can use this. This is a technique. Okay. Now, sorry. Now, since I was talking about local minima, minimum, let's say minimum, and local maximum. I was refraining to say maximum, minimum, or this is maximum value of the function. I was refraining from saying those words. Now I will tell you why. Let's take an example. Let's take a graph. I will explain why maximum minima wording can change. This confuses some all the students. What will be the absolute maxima? What will be local maxima? Relative maximum, like that. So let's take an example. Let's draw this graph. So this is like this. Let's say this is like this. Now you can notice. Let's draw the interval. This is A. This is B. This is C. And this is D. This is X. This is Fx. Right. Now, if you notice, here we have, it seems like we have a maxima. If we don't see the whole graph at once, we will say that this is maxima for this function. If we see only this region, we will say this is maxima. If we only see this region, we will say that this is minima of the graph, right? And this also seems like a minima, the endpoints. And this is again a maximum, right? Now, even this is also a maxima, and this is also maxima. Now, you might ask me why there are multiple maxima, then which maxima I will say is the right maxima. So, we can get multiple maxima, and these maxima are called, these maxima or extrema. Extrema means either maxima or minima. Extreme, sorry. These maxima or minima are called extrema. Extrema, either maxima or minima. So these maximum minimum which are inside the graph is called local or relative maximum, relative extrema. But to find absolute maximum or minima, we need an interval in which area we are talking about absolute maximum or minimum. If it is between A to D, then we can say that at x equal to D we have absolute maxima, right? We can see there, this is the maximum point of the function in this region, in this whole A to D domain. So for absolute maxima, we have to calculate all the maxima and including the endpoints. If it is part of the domain, then including the endpoints, and we have to make a table. In that table, we have to see the value of x and fx, which value corresponds to maximum among all the values. So whichever gives the highest maximum, that will be the absolute maximum, and other values which are like maximums will be local maximums, and whichever are minimums will be local minimums, and least value among all of them will be absolute minimum, right? So I will take an example so that you don't get confused. So let's take an example. Let's take an example. Let's see fx equal to x square. Let's take a simple example. Here point is not to take complicated example but to understand the topic. Okay, and our area of interest is, let's not write area of interest, interval of interest is in 1 to 4. Let's see, in 1 to 4 we are discussing its nature. Okay, now if we calculate f prime x, first we have to calculate first derivative to know the nature of the function. It will become 2x minus 4. If we equate it to 0, we will get x equal to 2. Now if we plot this x equal to 2 on the number line, this is positive infinity, this is negative infinity. Anything if we put lesser than 2, let's say if we put 0, then what we are going to get? If we put this region in this f prime x, we will get negative value, and in this region we will get f prime x as positive, right? So this is at x equal to 2, this is going from negative to positive. It was dropping, negative means it was decreasing. This is not value of function itself, it is value of derivative of the function. So derivative of the function was negative in this region, that means function was decreasing. Okay, now in this region function is increasing, so it was decreasing means dropping, and then it started rising after x equal to 2. So at x equal to 2, what we are going to get? This is minimum, right? Minimum of the function, not the absolute minimum, which may or may not be absolute minimum. That we will check now. We will make a table now. This is x and this is fx, and first put the extreme point 1 and 4, and between these extreme point end points put all the critical points. Here we had only one critical point, which was x equal to 2, so 2. Now on all these value, calculate value of the function on all these functions, on all these points, calculate value of the function. So what at x equal to 1, what we are going to get? Function is here, our function is here, actual function is here. So if we put x equal to fx equal to, let's write here x square minus 4x plus 9, this is our actual function. If we put x equal to 1, we will get 1 minus 4 plus 9 means 6. At x equal to 2, 4 minus 8 minus 4, we are going to get 5. At x equal to 4, 4 16 minus 16, we are going to get 9. So if you see this, in this region, this is absolute minimum, right? Absolute minimum. So this minimum value at x equal to 2 was actually absolute minimum, and this is highest point in this region. So we can say this is absolute maxima, right? In this region at x equal to 4, we are going to get absolute maximum of the value of the function, and at x equal to 2, we are going to get absolute minima of the function. So this is how we calculate local minima and absolute minima. This is also relative minima. Not to confuse, by any absolute minima is also part of minima, right? So relatively this is minima, and this is by fact this is absolute minimum. There cannot be any more minimum in this interval for this particular function, right? So this is how we calculate absolute minimums or absolute extrema of a function in any given interval. Now uh, another topic is, it's like a subtopic of this topic is, this video will become too large for the if I include here, so I will discuss that in next video. So in this video this much only, and you guys who are watching this video, please go and practice on these topics, practice on maxima minima and all these things. And in next video we are going to see double derivative test, so that we don't have to even plot this number line and put these values. So double derivative, we will calculate twice derivative of a function, and then based on the nature of the double derivative we will predict whether it will be minima or maximum. We will conclude whether it is minima or maximum, right? So till then, keep practicing. You can practice problems and get matching questions on our website mindspaneducation.com. Go to mindspaneducation.com. Here you will see all the courses. Go to calculus and optimization course. There you will see a lot of practice problem matching gate level, and it will be little higher than the gate level, so that you can practice and be ready for the exam, right? So see you in next video. Happy learning.